Anytime we're working with fractions, we want to be able to simplify them if possible. That's not going to change when we look at fractions that have variables in them. We're still going to want to simplify our answers as much as possible. To do that, let's remind ourselves of how we simplify just a simple fraction with pure numbers. For instance, 12 over 42. The rule for simplifying is we want to look for common factors in the numerator and denominator. So one of the best things to do is think about factoring out the 12. So 12 is 2 times 6. 42 is 6 times 7. When we look at those factors of the numerator and denominator, what we see is that the 6 is in common. And technically, we usually think about canceling them, but the reason that works is that when you pull this multiplication apart and think about this as being 2 times 6 over, and pull the 6's together, 7 times 6, what we have is 6 over 6, which is equal to 1. That's why it cancels, because anything times 1 is just that thing that's left. So 12 over 42 simplifies to 2/7 because that common factor of 6 cancels out, because it's really just 1. When we have variables in our fractions, we're going to do something similar. We're going to have to simplify or factor them to simplify. So when we have just a single term in both top and bottom, generally what we're going to do is look for what they have in common by just factoring the numbers and thinking about how many variables we have. So we have a 4 here. X squared means x times x, and y is just 1y. 12 would be 4 times 3. We've got a single x, and then 3 y's. Need to extend my fraction bar. And then when you think about what's common there, there's a single x common, so that's going to be taken away as a factor of 1, a single y in common. I can't cancel the other x in the numerator or the 2 y's in the denominator because they have to match up exactly. And then the 4's cancel. Again, it's canceling out, leaving a 1. Anytime you cancel, you're going to be left with a 1, technically. So what's left here in the numerator is an x and a whole bunch of 1's, but 1 times anything is just that x. And then 1 times 1 times 1 times 3 would be 3, and there's 2 y's multiplied, so that's y squared. In our next example, we don't just have things multiplied, we actually have a trinomial on both top and bottom. When we have trinomials or polynomials in the top and bottom, we want to factor it as we would any trinomial. So this is part of why we spent all that time on factoring earlier in the term. We're going to have to factor to simplify many rational expressions and functions. So to factor this trinomial in the top, we would split up the x's to x and x. Then we want to think about factors of -10 that add up to -3. I think that would be -5 and +2. Now it may take you a little bit longer to do that yourself, but the main thing is just kind of show the work off to the side on some scratch paper and then put the answer back in. In the denominator, it's a little more complicated because of the 3 in the front. So we're going to have 3x times x. Then you can either use trial and error or an AC method to determine what the rest of the factorization is. In particular, you want to have an x plus 2 times 3x plus 1. That will give you the 7x when you multiply it out. So once we have everything factored, then look at the whole fraction. We're looking for common factors in the top and bottom. And when you look closely, that x plus 2 in the top is the same as the x plus 2 in the bottom. So they can cancel each other out. Technically, again, what's left is a 1 when you cancel, because we're dealing with factors of 1 that relate to 1. And then what's left is going to be x minus 5 in the top and 3x plus 1 in the bottom. We no longer need the parentheses because the x minus 5 multiplied by 1 is just itself. So you don't need the parentheses to show that it's multiplying anything because 1 is just going to go away. Same thing with the 3x plus 1. Now be very careful here. Sometimes people want to try to cancel these x's that are left. There's one x on the top, one on the bottom. But remember, you can only cancel things if they're multiplied here. So the reason I could cancel the x plus 2's is they were multiplying what the other parts of the numerator and denominator. The x in the denominator here multiplies the 3, but it's added to the 1. So it's not truly a factor. It's actually part of a term in the denominator. Same thing for the x in the numerator. This is x minus 5. It's not x times 5. So this would be our final answer. We cannot simplify or cancel anything else in that fraction. When we work with rational functions, notice we have function f, g, and h on the page. We also want to simplify them if possible, but we're also going to be concerned with what the domains are. Let's take a look at our first example. If we look at this function f of x, we would always try to simplify it by factoring. The numerator would factor to a binomial times a binomial because we're working with a trinomial. The x is split up, and to get a negative 2 with two factors of negative 15, I would want to use negative 5 and plus 3. And then the denominator, again, a trinomial goes to a binomial times a binomial, x and x for the x squared. And then we want two factors of 5 that are going to make negative 6. Because 5 is positive, we want to use two negatives. In particular, negative 1 and negative 5 would multiply to the positive 5, but add to negative 6. Now that we have this factored, we can see that we have a common x minus 5 in both top and bottom. So those cancel, leaving 1. So this function actually simplifies quite a bit. It simplifies to x plus 3 all over x minus 1. Now the domain of a function like this, that is a rational function, it has a denominator, would be all real numbers except values that make the denominator 0. So what we need to exclude here definitely is x equals 1. So we have to say x cannot be equal to 1. But there's one other thing we have to exclude as well. Up here, when we simplified the function, we took out this x minus 5. Technically, the domain of a rational function has to be defined by the way it's initially written, so that x minus 5 also cannot be 0. So x cannot be equal to 5. Even though it no longer exists in the final function, we still have to think about this as an exclusion to the domain of the function. So we have to take out the 5 as well from our real number set that would create the domain. In fact, what a lot of people do, and in fact you should do, is you should say whenever you cancel a factor when you're writing out the function, is you should actually tell anyone reading that x cannot be 5. So you should list that exclusion. So typically when you simplify a function, if you've simplified something that could be 0, you must show the exception there. Let's look at another example. G of x equals x plus 3 all over x squared minus 9. First factor, so we have x plus 3 in the top, and the denominator is a difference of squares, so it will factor to x plus 3 times x minus 3. There was no way to factor the top, but when you look closely, that is exactly what we have in the denominator. So I can cancel those as a common factor. The numerator here is not going away, though. Remember, whenever we cancel something, we're left with a 1. And in this case, we have to write the 1. The 1 doesn't multiply anything, so you must keep the 1 in that numerator. So the numerator does not ever go away. So we get a simplified function of g of x equal to 1 over x minus 3. But remember, we need to show the exception that we canceled. So here, x plus 3 got canceled, so we need to remind the reader that x cannot be a negative 3 because of this cancellation. And then that will help us with the domain, because in the domain, we cannot have x be negative 3, but we also, based on what the simplified form, can see that x also can't be 3. So this would be the final domain of our simplified function. In our last example, we have h of x equals 2x minus 10 over 5 minus x. Always factor what you can. There is a 2 in common, so take it out, and you'll be left with x minus 5. And then in the denominator, notice that this is not in descending order. And one of the things when we were factoring is that I always said write things in descending order. And if you have a negative leading term, factor out a negative 1. So if we factor out a negative 1 here, let me write this down. So my numerator stays the same, but if I factor the negative 1 from the denominator, I'm going to get x left because negative x divided by negative 1 is positive x, and then 5 divided by negative 1 is minus 5. And what we see here is there really was a hidden common factor, that x minus 5 was common to both the numerator and denominator. And so we end up in the end with h of x equal to 2 over negative 1, which is just the same thing as saying negative 2. Now we do have an exception here. Because we canceled x minus 5, we have to say that x cannot be equal to 5. So our domain would be all real numbers except 5. So when you have a rational function, because it is a fraction, you always want to attempt to simplify it. Sometimes they will simplify, sometimes they won't. If they do, make sure that you show that exception in a way in the simplified result. And then that's going to be it's going to come up in your domain as well.